Okay, hello. We are going over limits review 3. Let's do it. Let me just see something really fast. That's not too bad. Alright, we go, the limit is x approaches 2 of x cubed minus 8 over x minus 4. Alright, this is a nice warm-up problem because, in fact, this is pretty easy. We've done problems like this before. If you try to plug in 2, you get 0 on the top, 8 minus 8, and that's x squared minus 4, and 0 on the bottom. How should we do this then? Well, we need to do some algebra. In this case, the algebra is to factor. The top is a difference of cubes, so that's x minus 2, x squared plus 2x plus 4, and on the bottom, I can write x squared minus 4 as x minus 2 times x plus 2. And so these things cancel, and the x minus 2's in particular cancel, and I therefore have a limit which is not anymore indeterminate. It's just x squared plus 2x plus 4 over x plus 2. And what is that? Well, when I plug in 2, I get 4 plus 4 plus 4, so that's 12 on the top and 4 on the bottom. And so the answer to this is just 3. Good. Next, number 2. Let's see, kind of get a little line going through here. There we go. Number 2 is the limit as x approaches infinity of 1 over 3 to the negative x. Alright, well this is a little bit of a silly problem because 3 to the negative x just means, by the definition of negative exponent, 1 over 3 to the x. So this is really just might as well be asking for the limit as x approaches infinity of 3 to the x. And the answer to this is just obviously infinity. If you want some kind of justification for this step, I think just a graph is sufficient. So that's kind of all I would do. Because this is just a known function, and it's just known that the end behavior is infinite. Okay, this number 3 also maybe a little bit silly. The limit as x approaches infinity of sine squared. Well, okay, what is sine squared going to do? It's just going to kind of go, up and down and up and down. How does it go up and down and up and down? Maybe that doesn't actually matter, but we can answer this question. This is maybe a good time to review this or something. That let's not forget our basic pre-calc that cosine 2x is cosine squared x minus sine squared x, but we can also write cosine 2x by subbing in 1 minus sine squared for cosine as 1 minus 2 sine squared x. And that means that I can solve for sine squared, and if I do that I get jom over 2, so in fact sine squared x is actually 1 minus cosine 2x over 2. I know you learned this last year, and I know I keep reminding you over and over again about this. That's because I think it's important and it's easy to forget. This is the so-called power-reducing formula for sine. It expresses the square of sine as 1 minus cosine 2x over 2. So what's the takeaway here? The takeaway here, this is sort of more work than was necessary, but really sine squared just actually is 1/2 minus 1/2 cosine 2x. And so the answer to this problem is that this limit does not exist. That's definitely the answer, but as for justification, you could probably even just write a sentence that said the function just goes up and down between 0 and 1, which is true. How does it do that? Well, by using the power-reducing formula, we see that actually this function is just a trig function, a sinusoid. It's a trig function with, it's a cosine 2x function, so that's pi over 2. The period will be pi. And what's it gonna look like? Well, it's going to be an upside down cosine with amplitude 1/2 moved up 1/2. So if you really wanted to make an accurate graph of this, what would you do? You'd graph an upside down cosine curve. So boom, boom, boom with amplitude 1/2 and period pi. And it's just doing this kind of forever. And so that's how you make an accurate graph of sine squared. But anyway, the answer is that this limit does not exist because as x goes to infinity, it does not approach some particular y value. Okay, 4 and 5 are really just the same problem. What's the limit as x approaches a from the right, and what's the limit as x approaches a from the left of absolute value x minus a over x minus a? Okay, well, maybe making some space kind of over here or something to talk about this for a minute. There's a couple ways to do this problem. The most important thing is, this is like the 4th time I'm reminding you of this fact during the video, via video from the first couple weeks of this class, but the so-called analytic definition of the absolute value function is that it's just always makes the thing on the inside positive. And so, if the thing on the inside is already positive or 0, leave it alone. But if the thing on the inside is negative, then put a negative in front of it, therefore making it positive. So, one way to approach this problem number 4 is to do it analytically. That is to say, we shall analyze the absolute value by analyzing it away, by getting rid of it. What do I know about absolute value x minus a? Well, it depends on whether the thing on the inside is positive or negative. In this case, since we're approaching a from the right, that means that for this problem, x is always a little bit bigger than a. And if x is always a little bit bigger than a, then necessarily the thing on the inside of the absolute value will be positive. And so this problem just becomes the limit as x approaches a plus of x minus a over x minus a. Because here I'm using the definition of the absolute value. The definition of the absolute value says, look on the inside, see whether the thing on the inside is positive or negative. In this case, it's negative. So, it's positive. So since it's positive, the absolute value of something positive just is that thing. And therefore, the answer to this problem is 1. Hold on, did I copy this problem down wrong? I totally copied this problem down wrong. I remembered the answer being something else. So, sorry, I'm here. It was x squared minus a squared in the denominator. Nothing I said so far is wrong. But anyway, that's where we are. So, I've already made some progress now because on this second step, I got rid of the absolute value. Now that that's gone, my life is a lot easier. This becomes the limit as x approaches a plus of x minus a over x minus a times x plus a. And so, this is just the limit as x approaches a plus of 1 over x plus a. That's because I canceled these. And of course, if x is very, very close to a, then this is just 1 over 2a, and there it is. Okay, number 5 is basically the same problem, but now I'm approaching a from the left. So, okay, if I'm approaching a from the left, then I have to recognize that x is always going to be a little bit less than a. And if x is always a little bit less than a, then x minus a will be negative. If x minus a is negative, then by the definition of absolute value, the absolute value of something negative is the opposite of that negative thing. So you have to have the kind of discipline and comfort level with this definition to just rewrite absolute value x minus a as negative x minus a. Why do I just write it as negative x minus a? Because I always just put a negative in front of the thing on the inside if the thing on the inside is negative, which it is in this case. Okay, so x minus a, x plus a. Here I'll do my factoring in advance. So this cancels, and then we get the limit as x approaches a minus of negative 1 over x plus a, And this time, therefore, the answer, if x is very, very close to a, is -1 over 2a. Okay, so this kind of happens a lot with absolute values, that we get kind of different answers depending on whether we're taking the limit from the left or from the right. And, well, okay, there it is. So I guess I was going to try to graph this, but now maybe I don't want to or something. Yeah, maybe I just don't even want to graph this, because I don't know what this graph looks like. All right, good. Number 6 then. So let me take this space back. What's number 6? This is just seemingly kind of a silly problem. If I plug in 0 for h, then that's just 1 minus 1. So that's a 0 on top and a 0 on the bottom, so it's a 0 over 0 situation. What can I do? Well, I have to do something. So here I'm going to sort of do the only thing I can do, which is just to expand this whole thing out. Okay, so remember, at the end of 2020, we learned the binomial theorem, and perhaps for numbers this small, 6 is right on the edge of it's probably faster to just do the triangle, but anything above 6, I might start cranking out some combination notation to find those binomial coefficients more directly. But here, okay, there it is, Pascal's triangle. The 6th row of Pascal's triangle, starting with the first row being 0, is going to give me the 6 coefficients, the 7 coefficients rather, for raising a binomial to the 6th power. So this becomes the limit as h goes to 0 of, what is 1 plus h basically? Well, it's going to be 1 plus, now it's going to be 6, well, okay, this is a little bit weird to do it this way, but okay, too bad. 1 plus h, so that's going to be, the coefficient is going to be 6, and then 1 to the 5th times h, plus 15, 1 to the 4th, h squared, plus another 20, I wonder if I'm going to be able to fit this, plus 20, 1 to the, let's see, oh man, I lost track, 5, 4, 3, 1 to the 3rd power, 8, it must be 1 to the 4th, h cubed, plus 15 times a bunch of 1s, h to the 4th, plus 6 h to the 5th, plus h to the 6th. I think I did that correctly. So all of that in parentheses, and then minus 1. And all of that is over h. Okay, so that got a little messy because I ran in a boardroom, but hopefully you can follow that. I just simply cranked out the binomial formula for 1 plus h to the 6th. Well, look, the 1's cancel now, and so what is this? It's the limit as h goes to 0 of 6h plus 15h squared plus 20h cubed plus 15h to the 4th plus 6h to the 5th plus h to the 6th. And if I divide that whole thing by h, now I can take an h out of every single term, and so this is the limit as h goes to 0 of 6 plus 15h plus 20h squared plus 15h cubed plus 6h to the 4th plus h to the 5th. And everything with an h in it goes to 0, and therefore the answer to this problem is 6. Alright, this seems a little bit silly, but we're going to do problems like this again very soon. Okay, good. Back in a second with more. Okay, here are 3 more problems, all kind of easy, to be honest. Number 7 says, what is the limit as x approaches negative a half of the floor of 3x? Well, this is a little bit of a letdown because, you know, there's just nothing going on. If you plug in negative 1/2 for x, then this becomes negative 3/2. And what is the floor of negative 3/2? Well, negative 3/2 being not an integer just has a very straightforward floor. It's just negative 2, so that's all there is to say. Limit as x approaches infinity of 3x plus 4 over root 2x squared minus 5. All right, this is kind of a repeat of a problem type that we did on Limits Review 2. So this is just more now of this. And what should we do? Well, it's not quite a rational function, but it's kind of like a rational function. So I want to divide by the highest power of x in the denominator. Since 2x squared is inside a radical inside the denominator, then it's kind of like the highest power in the denominator is x. And so what I'll do is I'll divide the top and bottom by x. Okay, and now what? Well, the numerator is just completely straightforward. It now becomes 3 plus 4 over x, so that is now clear. The denominator, well, if I'm being sort of very careful about this, what I kind of want to do is like combine the root 2x squared minus 5 and the 1 over x. And the way to do this is to recognize that 1 over x is really like root 1 over x squared. Is that actually true? Yes, when x is positive. So this holds since x is positive, then it is true that the square root of x squared is just x. In general, it's not true that the square root of x squared is x because for negative numbers, that formula doesn't work. But for positive numbers, that's true. And so my sort of conversion, so to speak, of this 1 over x into this is correct. Anyway, now I can simply just do it. So what do I get? I get 3 plus 4 over x over, and now this becomes one big radical in which I distribute through, and I get 2 minus 5 over x squared. And in fact, we get as our answer the thing that you were probably expecting anyway, just from eyeballing this. These both go to 0, and this numerator is looking a lot like 3, and the denominator is looking like root 2, and so the answer to this problem is just 3 over root 2. You can multiply by root 2 over 2 if you want, but I don't think we really have to. Okay, good. This one is kind of just the same thing, to be honest. So this is just sort of like another problem. So if I multiply the top and bottom by 1 over x and distribute that through, actually, do I want to do that? I guess I want to do something slightly different. I didn't even really pay attention to this. I guess I want to multiply through by like root 1 over x. Yeah. Yeah. So, alright, that was like a little bit interesting. So multiply through by this, even though, frankly, it's pretty clear. Well, maybe it's not that clear. I don't know. Okay, if I do that, what do I get? I get then the limit as x approaches infinity of combining those square roots. It is 1 over x plus 1 over root 9 minus 1 over x. And so this is going to 0. This is also going to 0. And as x goes to infinity, and so this is looking pretty much like root 1 over root 9, and so the answer to this problem is just 1/3. Okay, back in a second with the last 3. Okay, let's go. Here we are with the last 3 problems from Limits Review 3, 10, 11, and 12. And 10 and 11 are both basically the same thing. And they're both just a repeat of the last problem from Limits Review 2. Okay, you were supposed to watch that video on Limits Review 2, and it tells you how to do problems like this. And it's possible that you could have figured that out on your own, but you were expected to watch that video. So this is then nothing new. If I try to plug in a very, very large number here, well, what happens as x goes to infinity is that these both go to infinity. And so we have an infinity minus infinity situation. And I proved to you within Limits Review 2 video that infinity minus infinity is another one of the indeterminate forms. So I can't conclude anything from that. I need to get into the details of the algebra. Okay, what are the details? What is the gap between these two, if any, as x goes to infinity? Well, there's only one way to unlock the sort of information about what the square root of x squared plus 3x really is. The answer, if you have something sort of locked inside of a square root, you must unlock it. And we have to kind of find some way to square this expression. That's what the square root of x squared plus 3x is. It's the number which, when squared, is x squared plus 3x. So how? You multiply by the conjugate. So this is perhaps not totally natural thing to do until you recognize that it's really the only way to unlock the difference between these two. And okay, once you do it, you see that it just works. Well, all right, let's go. What happens? Suddenly, I have the square root gone, or at least in the numerator. Turn this on, maybe. In the numerator now, I have x squared plus 3x, because it's just difference of squares, minus x squared. So that's looking really good. And in the denominator, I just have this, root x squared plus 3x plus x thing. All right, so what does this turn out to be? It turns out to be the limit as x goes to infinity of just 3x over root x squared plus 3x plus x. And here you can perhaps already tell what the answer is going to be. But we will treat this like the almost rational function that it is, and we'll divide the top and bottom by the highest power of x in the denominator. And okay, what do we get? Well, we get the limit as x approaches infinity of, on the top we get just 3, and on the bottom, distributing this 1 over x through the radical and sort of skipping steps a little bit, I guess, that becomes kind of like 1 over x squared when you put it back in jail. So this becomes root 1 plus 3 over x, and then that's just like plus 1. Yeah. So the answer is that as x goes to infinity, 3 over x goes to 0, and so this is going to 3 over root 1 plus 1. So that's just like 3 over 1 plus 1, so that's just like 3 halves, and that's the answer to this problem. Okay, that is like completely correct. However, you might find it a little bit unsatisfying because it doesn't kind of like explain what's really going on here maybe fully. Is there another way to do this problem? Kind of, yes, although I don't recommend it. The other way to do this problem, so here's now like an alternative solution or something like that. The alternative solution is take x squared plus 3x, this thing under the radical, and complete the square. How do I do that? Well, half of 3 is 3 halves, so I sort of like add 9/4 and subtract 9/4 again. All of this is happening under the square root, so I'm doing some kind of side calculation algebra now. Therefore, another way to do this problem, perhaps I'll do it in purple, is to say that the limit as x approaches infinity of the square root of x squared plus 3x minus x is, upon performing a sort of algebraic manipulation of the thing inside the radical, this is really like the limit as x approaches infinity of the square root of x plus 3 halves squared minus 9/4 minus x. Cha, cha. And now it seems okay, that's how I'm going to put it, to say that for very, very large values of x, that x plus 3/2 squared is going to dominate over this minus 9/4 to such an extent that this might as well basically becomes the square root of x plus 3/2 squared minus x. In other words, I am getting rid of the 9/4 because it's irrelevant eventually for large enough values of x. And so this is really like x plus 3/2 minus x, and therefore this is 3/2, which is the answer. So this is kind of an alternative solution, which you might prefer actually, because it sort of explains at perhaps a deeper level what's really happening here. So here's the beginning of my alternate solution. This quadratic underneath the radical, perhaps the best way to understand any quadratic is to kind of complete the square on that quadratic and sort of reveal it for what it really is. And this is really like x plus 3/2 squared, give or take a constant. And so this entire first term might as well just be x plus 3/2. And therefore, as x goes to infinity, this is going to 3/2. Okay. Cool. For number 11, however, I'll just do it the traditional way. I don't think I have anything more to say, so I'm just going to do this problem. What do? It's an infinity minus infinity situation, so I'll multiply by 2x plus root 4x squared minus 5x over 2x plus root 4x squared minus 5x. And when I do that, then what happens, kind of moving down here a little bit, that gives me the limit as x goes to infinity of 4x squared minus 4x squared minus 5x. Cha, think I did that right? Yep. All over 2x plus root 4x squared minus 5x. And continuing over here, that gives me the limit as x goes to infinity of 5x over 2x plus root 4x squared minus 5x. And just like before, this is almost a rational function, so we can treat it like a rational function by dividing the top and bottom by the highest power of x in the denominator. And if I do that, then I get the limit as x goes to infinity of 5 on the top, and on the bottom, distributing this 1 over x through to the 2x gives me 2, plus distributing this 1 over x through here, maybe this time I'll show my work. This 1 over x is really like root 1 over x squared, so perhaps you can just do all this in your head, but as I did above, but if not, then this time I'll show the steps. I convert this 1 over x into root 1 over x squared, which is legit because x is going to infinity. And now finally, this becomes the limit as x goes to infinity of 5 over 2 plus the square root of. When I distribute that 1 over x squared through, I get 4 minus 5 over x. And as x goes to infinity, 5 over x goes to 0. And so this is pretty much turning into 5 over 2 plus root 4, or 5 over 2 plus 2, or just 5/4. Okay. Good, good, good. Okay, now we get to the sort of hardest problem from this whole worksheet, I think by far, and the thing that's like sort of profoundly new is this one. The limit as x approaches infinity of x squared times sine 1 over x. Alright, so here's just like another one of these functions, these crazy functions which are a product of two functions. And so you might be thinking, well, okay, can't I just split this up? That's a good idea, maybe. So this is a product after all. So let me split it up into the limit as x approaches infinity of x squared, and the limit as x approaches infinity of sine 1 over x? Well, like, I don't think so, right? That's just simply not going to work. What is the limit as x approaches infinity of sine 1 over x? Well, we're sort of used to thinking of sine 1 over x as a function that I care about near the origin, and we've used it as an example of a function that doesn't have a limit near 0. And, well, what does this function look like? It's bounded between -1 and 1. It's odd because it's the composite of two odd functions. But, of course, as x goes to infinity, then you're taking the sign of a tinier and tinier thing. And so the end behavior of this function is definitely 0. And so we get something that looks like this, and then in between. Okay, but what's relevant to us right now is that as x goes to infinity, x squared goes to infinity, and this goes to 0. And so now I have no idea what's going on, right? This is a infinity times 0 situation, and we explained quite thoroughly, I think, last week that this is an indeterminate form. I cannot determine what this limit is based only on the fact that it's of the form infinity times 0. So this was a kind of a honest attempt to solve this problem by splitting it up into two pieces, but it doesn't work. Because I just don't know what infinity times 0 is in general. So I have to abandon that approach and try something that treats these two pieces kind of individually. And yeah, it's very not obvious what to do here. In fact, maybe it's time to kind of make another picture. And here's another picture. It's the very graph that I'm trying to make, right? This curve y equals x squared sine 1 over x. What does it look like? Well, you know, I can observe that. Oh man, sorry, some sort of knee injury. But sine 1 over x is certainly between -1 and 1. So multiplying through by x squared gives me that x squared sine 1 over x is between x squared and negative x squared. So that's kind of interesting. That tells me that if I want to graph this function, then I need to look at the envelope. And actually, I have graphed this function before in class. I believe this was the example I used when I demonstrated the usefulness of the squeeze theorem. And the squeeze theorem says, okay, well look, sine of 1 over x is odd, x squared is even, their product is odd. So something's going on out here, but I don't know what. And then it's going to go to and then something like this. But okay, I haven't answered the question. I've just kind of reminded myself that I don't know the answer to what is the end behavior. All right, let's finally settle this. Let's do it once kind of informally and once kind of more formally. The informal way to do this, let's see. The informal way to do this is to recognize that there's really only one thing that I know. The one thing I know about sine is that if you take the limit as theta goes to 0 of sine theta over theta, that's 1. And we sort of very carefully last week rather, proved this fact because we need it so much. And what does this fundamentally say? This fundamentally says that the sine of a very tiny thing is approximately that thing when that thing is basically 0. This is kind of the takeaway. So now I'm ready to understand this problem because as x goes to infinity, 1 over x is a very, very tiny thing. And so the sort of deep way of doing this problem and not writing much down on your paper is just to say that, look, sine 1 over x is pretty much just 1 over x. When x is very, very big. Okay, so for very, very large values of x, 1 over x is very tiny, and I know that the sine of something really, really tiny just is that tiny thing. And so the very casual way of doing number 12 is just to say, okay, look man, this sine 1 over x is basically just 1 over x. And so you're basically just telling me to take the limit as x goes to infinity of x squared times 1 over x. And that is just x, and that's just infinity. Okay, that is like pretty good. I would call that 90% good. If you crave a little bit more explanation for why that's true exactly, then what we can do is to perform like a limit switch. Limit switchy. So in other words, let's change this variable and replace this 1 over x with something else. So like let y be like 1 over x, for example. And now observe that as x goes to infinity, y goes to 0 plus. And therefore, I may rewrite this limit in terms of this new variable, and this limit is therefore equal to, well, as x goes to infinity, y goes to 0 plus. And in place of x squared, well, what is x squared? X is just 1 over y, of course. X is just 1 over y. So x squared is just 1 over y squared. So this becomes 1 over y squared times sine of y. And therefore, this is the limit as y goes to 0 plus of sine y over y times the limit as y goes to 0 plus of just 1 over y. And this, we know, goes to 1, and as y goes to 0 plus, 1 over y goes to infinity. And so the answer to this problem is definitely infinity. So I'm going to put a box around this because this is the answer. What we did over here is in some ways almost better, the more casual approach, because it reveals that it really is true that sine 1 over x is pretty much just 1 over x. And so I sort of get the answer to two questions. The limit as x approaches infinity of this function, it is infinite, but also it's infinite like in an x-type way. Okay? In other words, this function grows linearly. And what we have actually is like a slant asymptote of y equals x. So when it comes to, if what I really cared about was making an accurate graph of this function, then now I know two things. That, I'm not claiming this graph is super accurate, but it's like decently accurate that not only does this function go off to infinity as x goes to infinity, but that it goes off to infinity like the y equals x function. And so it's gonna, if you zoom out and zoom out and zoom out, it's gonna look a lot like the line y equals x. And since it's odd, I can tell you what it's doing on the other side as well. Okay, that was the last problem. Goodbye.